Dear friends, welcome to Rajshekhar classes on applied data science with Python. This is lecture number 397. In this lecture, we will try to understand Gini impurity. The other very important idea in information theory is Gini impurity, which is very similar to entropy. Very similar idea, but it has couple of advantages that we will see. So Gini impurity is written as I subscript g for a random variable y, that I can write it as ig of y. This is I subscript g of y, that is important for random variable y. What it says, Gini impurity is written as I subscript g of y for a random variable y. Isn't it? One must understand these are not same. I subscript gy means what? This one is Gini impurity. Gini impurity. What about Gini impurity? What about this? This is information gain. Information gain. But in my previous lecture, in lecture number 396, there is some mistake. In that lecture, we were saying that this one is Gini impurity, but if you speak strictly, it is information gain, and this one is Gini impurity. Please observe that simple correction. Yes, remember, don't get confused. Ig of y, this is I subscript g of y. I subscript g of y is Gini impurity of y. What is this? This is Gini impurity of y. Whereas this one is information gain. Information gain, isn't it? So if you have a random variable y, let y be a random variable which has k categories, y1, y2, so on, yk. The Gini impurity of y is defined as 1 minus Gini impurity of y means I subscript g of y, 1 minus summation I equal to 1 to k probability of y squared. Much more elegant, isn't it? Which this is much more simple than, this is simple. This is simple than what? Simple than our entropy. This one is simple than entropy, isn't it? So let's take a simple case. If you have, let's assume you have a random variable y. Let me assume y is a random variable which takes two possible values. One is positive class y plus and another one is negative class y minus. Let me consider case 1. What is case 1? Let me assume your probability of y plus is 0.5 and probability of y minus is 0.5, equiprobable. Now what happens to your Gini impurity? Gini impurity is I subscript g of y equal to 1 minus p of y plus whole square plus p of y minus whole square, means 0.5 whole square, this one, and this one is also 0.5 whole square. Therefore what will you get? 0.25 plus 0.25. Ultimately what is this Gini impurity value? You are getting 0.5 for equiprobability case. If both cases are equiprobable, what is my, just try to recall what is our entropy for equiprobable case. Entropy is 1. Therefore if positive class and negative class are of equal probability, you are getting information gain as 0.5, whereas entropy is 1. Just try to remember this. Yes. Now let me consider another case. I am assuming probability of y plus is equal to 1 and probability of y minus equal to 1. In that case, what is your information gain? 1 minus probability of y plus whole square plus probability of y minus whole square, means you will get your Gini impurity is 0. Remember, entropy of y. What is entropy of y in this case? Entropy of y is 0. Let's assume you have two categories, case of y plus and y minus, such that probability of y plus is equal to probability 1 minus probability of y minus. how does my entropy looks like? Entropy looks like this. Just let's plot this one. Just see, my entropy has maximum value 1 corresponding to the probability of 0.5. Just see, h of y equal to entropy of y 0.5 plus log of 0.5 minus 0.5. What is your entropy value here? Your entropy value is entropy value is 1. When will it be 1? If p of y plus is 0.5, your entropy value, this is my entropy. This is my entropy value is 1. Isn't it? What about information gain? Your information gain for this is information gain. Your information gain is 0.5. This is information gain curve. This above one is entropy curve, isn't it? For equiprobable case, h of y is 1. That's what it says. For information gain is 0.5. That's what it says. This is information gain. This one is entropy curve, isn't it? Now just see, your Gini impurity. This is your Gini impurity. What is this? This is your yes. What is this? Yes, just a minute. Okay, this is your Gini impurity. Looks like this. Gini impurity maximum value is 0.5. Yes, that's what it says. If you notice, Gini impurity and entropy are very similar, isn't it? In the region between 0 and 0.5. Just observe, in the region between 0 and 0.5. This region. In the region between 0 and 0.5, as p of y plus increases, isn't it? As p of y plus increases, both entropy and information gain. Just see, both entropy is also increasing and information, this entropy is increasing, also information gain. This region in between 0 and 0.5, your information gain Ig is increasing, also your entropy is also increasing. Between 0.5 and 1, what happens between 0.5 and 1? This is decreasing. Which one is decreasing? Information gain is decreasing, and also entropy is decreasing. So if you look at it, a very similar in concept, then you might, what does it mean? Then you might ask, why are we studying Gini impurity? Why do we care about Gini impurity? Why can't we use simply entropy, that is h of y? One small catch, formula for entropy. What is the formula for entropy? This is the formula. This is the formula for entropy. What is this? One small catch, formula for entropy. If you look at formula for entropy in 2-class setting, you have a small tricky thing. What is this? This is h of y equal to minus p of y plus log of p of y plus base 2, and minus p of y minus log of py minus base 2, isn't it? This is the formula. This is the formula for entropy, isn't it? Yes. What is the formula? In similar manner, what is the formula for Gini impurity? This is the formula for Gini impurity. In the case of h of y, we have to calculate logarithm. Just see, here we have to calculate logarithm. Here also we have to calculate logarithm. In the case of information gain, there is no logarithm. Just see, here in the case of information gain, there is no logarithm. Computationally, log takes more time compared to square. Here you have square. Here you have say this is log. Log takes more time. This log takes more time. This square term will take less time, isn't it? That's what it says. Just see, problem is in h of y you have log, but Ig of y in Gini impurity there is no log. Computing log takes more time compared to square. Computing log slightly more computationally intensive than finding squares. If both of them are behaving very similarly, as we saw, information gain is faster to compute, more computationally efficient to compute. Which one? Information. Gini impurity. not information gain. Gini impurity is faster to compute, more computationally efficient to compute than your entropy, because it does not have log. Your Gini impurity does not have log. There is no log term. Log takes more time to compute than squares. In modern decision trees, people don't use entropy as much. Of course, you can choose to use entropy. People typically end up using Gini impurity as a measure, as an alternative to entropy, and this works very, very well. Gini impurity works very, very well. If you look at most standard packages like scikit-learn implementation of decision tree, the default metric that it uses to construct a decision tree would be Gini impurity and not entropy. Of course, you can always use entropy. Both of them are very related concepts, but using Gini impurity is computationally efficient and faster. I request all of you go through this lecture. If you have any difficulty, please keep a comment. Thank you very much.